Open your eyes wide. Today, we are going to undertake a journey to the confines of the known universe, as far and as large as it is possible to go, starting from what we have at hand. Let's say a human being, infinitely average, immediately crushed by the monumental dimensions of the pyramids of Khufu, themselves 65 times smaller than the massif of Everest, which, compared to Calypso, Epimetheus, Hyperion or Miranda, one of the moons of Uranus, pales in comparison. And we could continue for a long time to climb the scales of increasingly imposing spherical bodies that we find in our solar system. And now, here is our Earth, a world on which, by walking vigorously at a rate of 30 kilometers per day, non-stop for 2 years, you could hope to make a journey of the order of something like that. And although it is individually impossible for us to explore all its nooks and crannies in an entire and well-filled life, the Earth remains ridiculously small compared to the gas giants that we find in our system, and which would all fit without problem, lined up in the space that separates our planet from the Moon. And all that we have just talked about is nothing compared to the dimensions of the Sun, which, with its diameter of 1,391,000 kilometers, is wide enough for us to fit 10 times the giant Jupiter, or 109 times the Earth. And yet this star is just a yellow dwarf, a name that makes sense when confronted with the waist size of stars such as Arcturus, Aldebaran or Rigel, all of which would overshadow it, although having a derisory diameter if we compare them to Antares, Betelgeuse or Uiskuti, the largest star in the known universe, which, with its radius 1,700 times greater than that of our Sun, towers over all the stars we have just talked about, and all of which, including Scuti, are actually of a derisory size compared to that of something in which we are all, the solar system. To try to touch on its immensity, let's go back to the scale of our Sun and confront it with Mercury, the first of the planets in the system. In this image, the proportions are well respected, but the distances, they are not. And when they become so, Mercury, once positioned on its orbit, is visually reduced to the size of a few pixels. And replacing the Sun with Arcturus, Aldebaran or Rigel in no way allows us to reach the orbit of the small planet. By taking some distance to accommodate the rest of the procession, we realize that with Antares, the orbits of Mercury, Venus, Earth and Mars would all end up inside the star, whose surface would still be far from reaching the first of the gas giants. That the giant Betelgeuse would barely lick. As for the monstrous Uiskuti, its surface wouldn't even reach Saturn's orbit and would still be distant from Neptune by a few 3 billion kilometers. A number that is extraordinarily difficult to represent. That's why, increasingly confronted with abnormal enormous distances, we're going to have to start talking in light time to get from the surface of the largest star in the known universe to that of Neptune. A grain of light, the fastest thing in the universe, would take 3 hours. 3 hours in space at 492 miles for S. Straight in space at the prodigious speed of 299,792 kilometers per second. To try to represent this properly astronomical speed, tell yourself that the time you blink once and a grain of light could make a round trip of the Earth. Let's pause for a second 3 on this idea. And there she has gone from the Earth to the Moon. But let's return to our immensity, of which Neptune is merely a beginning. To think bigger, we need to go further to meet the Voyager 1 probe, which is currently the man-made object furthest from our world. Launched in 1977, this probe has been hurtling through space at about 62,000 kilometers per hour. After 42 years of travel, progressing 160 times faster than a Formula One car, it has only reached a distance from the Sun about 6 times that of Neptune. In 2012, Voyager 1 surpassed the limit of the heliosphere, the bubble of influence of solar winds, and has since been traveling in the interstellar medium. Yet, although it is some 22 billion kilometers away from our star, it has not even yet traveled the equivalent of a light day, and is still far from having left the system which, taken in the strong sense, includes all celestial objects orbiting the Sun. And everything we just talked about now fits here. In this scale image, we can see the orbit of Neptune. And there, the current position of Voyager 1 compared to Sedna's orbit around our star. This trans-Neptunian object, almost 10 miles wide, has an orbit of immense proportions. When Sedna passes by here, it is then 5 times further away from the Sun than Voyager 1 is today. Yet, even then, this dwarf planet is still in our system, because the gravitational pull of our star extends over much, much larger distances. To truly extract ourselves from it and hope to reach its outskirts, we will have to cross a cloud of enormous dimensions. A cloud towards which Voyager 1 is currently heading. And everything we've just talked about appears ridiculous and now fits entirely in this small bubble, where we can distinguish Sedna's orbit compared to the dimensions of the Oort cloud. A collection of dust, ammonia ice, methane, water, and billions of comets that surround our star like a sparse bubble. It is estimated that Voyager 1 should take at least 1,200 years before reaching the inner edges of the cloud. And between 20,000 and 30,000 years, once entered before exiting, to finally surpass the gravitational boundary of our system. The probe will then have only traveled a distance equivalent to a quarter of that which separates us from the closest star to us, the modest red dwarf Proxima Centauri, located only 4.2 light-years from the Sun. In this image, with its poignant emptiness, the stars are not to scale, because their size would then be smaller than a pixel. As enormous as the scales we have reached may be, there exist in the universe objects, or rather structures, whose dimensions can rival or even exceed everything we have just flown over. To convince ourselves, let's welcome to scale the Cat's Eye Nebula, the Eskimo, the Alea, the Dumbbell, or even the Helix, which spreads over distances of the order of those that separate us from Proxima. The enormity of this image is expressed in each small frayed gas structure that we observe on its outskirts. Because each filament here is larger than the size of our inner solar system. As for the Crab Nebula, a structure made up of flows of stellar matter ejected by the explosion of a star that has now disappeared, we would still need to step back to grasp all its immensity. Obviously, not all of these nebulae are found in our immediate vicinity, and proximity does not necessarily mean visibility. With distances, apparent brightnesses melt away like snow in the sun. Consider that a hypothetical observer, located 50 light-years away from us, and with vision substantially identical to ours, would not see our sun. Proxima Centauri, although it is 10 times larger than our world, is still, on the scale of space, literally next door. And for us, from Earth, invisible to the naked eye, and was only discovered through telescopes in 1915. Of the 6,000 stars that can be seen with the naked eye, on clear moonless nights, only 133 are located less than 50 light-years from us, while we have been able to count the presence of 1,800 through our telescopes. Around 1/3 are situated within a 250 light-year radius region. And almost all of those visible without technical assistance fit into this small sphere, a region with a radius of 1,000 light-years, which is just a tiny part of the Milky Way, our galaxy, a structure that's 100,000 light-years wide and 1,500 thick. To get a sense of its size, imagine that if we reduced the Sun to the size of a red blood cell, while keeping the proportions, the Milky Way would then be as big as Europe. And as strange as it may seem, our galaxy is part of one that we will probably never see in its entirety. Because to hope to reach a point far enough away to take a picture, capturing it in its entirety, it would take, at the speed of the Voyager 1 probe, some 550 million years. All the images you will see of it, like this one, will only ever be artists' views. Reconstructions made from the data collected, from the inside, from where we are, 25,000 light-years from the center. From Earth, our modern telescopes, by scanning the sky, give us a splendid glimpse of the some 300 billion stars we think it contains. They also allow us to discover structures whose dimensions rival those separating us from nearby stars, such as the Orion Nebula, here compared to the distance from the Sun to Proxima, itself compared to the Rosette Nebula, or even the Carina Nebula. All these sheets of dust, gas, and stars are part of our galaxy, which was at the beginning of the last century, the only one in the known universe. Today, we have trouble estimating the number. In the universe, they are found everywhere. And this, whatever the directions where we look. A few years ago, astronomers pointed the Hubble Space Telescope towards an extremely dark and small corner of the sky. To the naked eye, its apparent size is equivalent to the distance of a pinhead, held at arm's length. And after 1,000,000 seconds of exposure time, they got this. One of the most extraordinary photos ever taken by humans. A small number of the bright points that we see are nearby stars in the foreground. But the rest, all the rest, is just galaxy. In this single snapshot, by finely analysing all the data, we were able to identify nearly 10,000. And this photograph is just a piece of the ridiculous, a tiny portion of the sky represented here, next to the moon. It would take about 23 million photos like this one to cover the entire celestial vault. Our Milky Way is therefore not alone, and the bestiary of galaxies of which it is part includes an astronomical number of objects of various shapes and sizes. Some, like Zwicky 18, are irregular and barely larger than a nebula, 6,000 times brighter than that of Orion, to which it is compared in size, New General Catalogue 604. This so-called triangle nebula is nothing more than a spot among dozens of others on the scale of its high galaxy. Here compared to M82, which although twice smaller than ours, is 5 times brighter due to the exceptional rates of star births taking place there. As for 1104, the so-called Sombrero Galaxy, it has a heart of bewildering intensity that gives it a hat-like appearance. This is the typical elliptical galaxy Oaks, encircled by its peculiar ring of blue stars. Depending on their age, their history, and their past interactions, these giants of space can see their size grow, their shape change. The tadpoles must surely owe its barred spiral appearance, one of whose arms has literally dislocated to one of its interactions. As for M87, it must have ingested and merged with many of its kind, to the point of reaching a mass 200 times greater than that of our Milky Way, here on a comparative scale. But M87 is nonetheless a sketch of gigantism compared to the colossal Hercules A, equipped with impressive jets of matter and energy coming from a hyperactive black hole hidden in its center. This galaxy, although 1,000 times more massive than ours, is nonetheless twice as light and 4 times less extended than the one that remains to this day the largest galaxy in the known universe, IC 1101, a monster housing more than 100,000 billion stars. But once again, by comparing details too much, we lose sight of the positively monstrous distances that separate all of this. So how far away are all these galaxies from us? And how are they distributed in space? To try to touch on this, let's represent, as seen from Earth, the surface that the Andromeda Galaxy would occupy in the sky if it were slightly brighter. Located 2.5 million light-years away from us, Andromeda is part of our galactic neighborhood, our local cluster. In cosmic terms, it's our next-door neighbor. In terms of scale, it's twice as big and contains 3 times as many stars as ours. To cover the distance that separates us, the Voyager 1 probe would take 56 billion years. A length of time nearly 4 times longer than the age of the universe. When we talk about close neighbors, we have to put a lot of space in quotation marks. Here is an overview of our local cluster. The distances and sizes shown are approximately proportional. It includes Andromeda, the Milky Way, as well as a procession of about 50 other galaxies of smaller size. And by zooming out by a factor of 10, all of this becomes just a tiny part of an even larger whole, which includes over 1,000 galaxies. This is what we call our local group. In this image, spanning 100 million light-years, each white spot represents at least one, if not several galaxies. But our local group is itself only a subset of a colossal structure, the Virgo supercluster, whose staggering size is estimated to be 150 million light-years in diameter, and which contains some 10,000 galaxies distributed in about 100 clusters, among which we find ours and that of Virgo, distant by nearly 60 million light-years. And here this supercluster itself is contained in an even larger structure, and we begin to see, at ever larger scales, lines of higher density and dark areas, voids such as that of the Bootes, where there are only a few dozen galaxies in all, distributed in a volume nearly twice as large as the Virgo supercluster, which contains more than 10,000 of them. Here, space definitely lives up to its name. And our local supercluster is just one among many, as the number of such structures is estimated to be several million. Everywhere you look, no matter the direction, there are superclusters which, when taken together, form, on a very large scale, something like a huge spider's web. And everything we've just talked about is now a small point in the center of the observable universe, which is estimated to contain between 100 and 2,000 billion galaxies. Beyond the edges of this image, the deafening geography of the known universe stops visually. But the universe continues. We have not reached a limit, an insurmountable border. These confines of the cosmos only mark the perimeter of a sphere with a radius of 45 billion light-years, which includes all the galaxies whose light has had time to reach us. Beyond this cosmological horizon lie billions of other galaxy superclusters, as the universe itself continues to expand. How far and when does it stop? We don't know. It is likely that this immensity, already incredibly difficult to grasp, is itself ridiculously small compared to the size of the entire universe. It's even possible that it never stops, that the universe is infinite, and the dimensions of this beyond are themselves beyond anything the imagination can conceive. Because infinity is an idea without an image. Some people on Earth don't enjoy contemplating the universe and the vastness beyond our world. Others love the vast knowledge. They fill them with paradoxical emotions, shivers experienced in front of these immense skies, in turn crushed, anxious, or exalted, seized by this sidereal and stunning void. These expanses move us, soften and damage our equals, making us understand that we are only humans, on a planet, in a galaxy, and perhaps even within a universe among so many others. And sometimes they elevate us above ourselves and force us to worry about the essentials. To write to us, it's simple, observable universe. Local supercoaster, Virgo supercluster, local galactic clusters, spiral galaxies, Milky Ways, Orion's arm, 25,000 light-years from the center, solar system, third terrestrial planet from the star, Earth. These videos would not see the light of day without the precious support of all those who, on TP, Utip, or via the join button, allow us to devote ourselves to it full-time. If you stayed here, it's because you wanted to be sure that a photon that left the surface of the Sun at the beginning of this video had time to pass the orbit of the Earth. Unless it's to find out how we manage to measure the distances that separate us from objects that are so staggeringly far away from us. So here are, in broad strokes, represented in a somewhat caricatured way, the methods we use. First of all, when objects are relatively close to us, like the Moon, we have the technique of radio echo. The principle is straightforward. We aim waves at an object, and when they reach it, a tiny part bounces back to us. And since we know the speed at which these waves propagate, we deduce, based on the time they take to return to us, the distance of the bombarded object. This method measures the distance between Earth and the Sun or Moon. On the latter, one of the Apollo missions even left a small mirror on the surface, a laser reflector, which allows us to measure with an accuracy of a few centimeters the distance that separates us from our satellite. For more distant objects, such as nearby stars, we use the so-called parallax method, which involves studying the movement of a star from two observation points, far apart from each other. And since our planet revolves around the Sun, it is enough to carry out these measurements 6 months apart, so that the two observation points are 300 million kilometers apart from each other. During the second measurements, the angle of sky observation is slightly modified. And knowing the Earth-Sun distance, we can calculate, thanks to Pythagoras' theorem, the one that separates the Earth from the observed star. But this technique only works for objects located at most only a few hundred or even thousands of light years away. And when the distances to measure start to become frankly significant, we are interested in variable stars called Cepheids. These stars, 4 to 15 times more massive than the Sun and 100 to 30,000 times brighter, have the peculiarity of having a brightness that varies over time, according to a well-known rhythm. By studying the link between the pulsation rate and the brightness of Cepheids relatively close to us and comparing them with those further away that also beat time, with metronome regularity, we can, based on their difference in brightness and after some clever calculations, deduce their distance. This method works well for measuring things up to galaxies close to ours, but to be able to go even further, astronomers study the death of certain stars that occur in very specific configurations. These cataclysmic explosions, called type Ia supernovas, always occur in binary star systems, which, engaged in a game of matter exchange, end up seeing one of the two stars transform into a white dwarf, which will then absorb the upper layers of its imposing neighbor, transformed into a red giant. The matter, as if sucked up by the smaller star, accumulates there until it eventually explodes, invariably after reaching a critical mass that is always the same. And since these explosions always produce the same intrinsic brightness, they therefore become a kind of standard candles for astrophysicists, who by studying the amount of light received by our telescopes can estimate the distance at which the supernova is at the time of its death. With that, all good things come to an end, except this episode which had two.